All right, welcome to The Explainer. Today we are diving headfirst into something that sounds like science fiction, but is very, very real: quantum computing. This isn't just a faster computer, it's a completely new way of processing information that could change, well, pretty much everything. Okay, so think about this. Every single piece of tech we rely on, your phone, your laptop, even the biggest supercomputers on the planet, they all play by the same set of rules. But what happens when the problems get too big, too complex for those rules? We're finding that for some of the world's most massive challenges, our computers have in fact hit a wall. To really understand why we need this quantum leap, we have to first get a handle on the dead end we're staring at. Don't get me wrong, classical computers are incredible, but they have a fundamental bottleneck, something baked into their very design. And it all boils down to this: the core difference between a bit and what we call a qubit. A classical bit is dead simple. It's a light switch. It's either on or off, a 1 or a 0. That's it. But a quantum bit or qubit, that's more like a dimmer dial. It can be a 1, it can be a 0, or, and this is the mind-bending part, it can be both at the exact same time. That both at once thing, that's the secret sauce.
So why does that even matter? Well, because our classical computers, as fast as they are, just completely choke on problems where the number of possibilities explodes. I'm talking about things like simulating a single complex molecule for drug discovery or finding the absolute best route for thousands of delivery trucks all at once. For a normal computer, the possibilities become astronomical. And we can't just keep shrinking transistors forever. Moore's law is slowing down, so we're hitting a very real physical limit.
So, to smash through that classical wall, we have to play in a whole new sandbox, a different realm of physics. And the rules here, well, they are famously weird. They are bizarre and they make no sense to our everyday intuition. So, buckle up. Welcome to the world of quantum mechanics.
The first big rule is called superposition. This is that dimmer switch idea. Because each qubit can be both a 0 and a 1 at the same time, a quantum computer can explore a huge number of possibilities all at once. A few hundred qubits can look at more combinations than there are atoms in the known universe. It's a kind of parallelism that classical computers can literally only dream of.
And if you thought that was weird, the second principle is even stranger. It's called entanglement. This is where you can link two qubits together so their fates are perfectly intertwined. I mean, no matter how far apart you pull them, across the lab or across the galaxy, if you measure one of them, you instantly know the state of the other. It's a perfect, instantaneous connection.
This idea was so bizarre, so completely against how we think the universe should work, that Albert Einstein himself couldn't buy it. He famously called it spooky action at a distance. He just couldn't accept that it was real. But guess what? It is. And that spooky connection is an absolutely critical resource for quantum computing.
Okay, so you've got these two bizarre properties, superposition and entanglement. What do you actually do with them? Well, you have to build completely new kinds of recipes, new kinds of instructions. We call them quantum algorithms, and they're specifically designed to harness all that quantum weirdness and unleash it.
And you know, this isn't brand new. These ideas have been brewing for decades. It started with the physicist Richard Feynman just musing about it back in the 80s. Then in the 90s, guys like Peter Shor and Love Grover came up with the killer app algorithms on paper. And then, in 2019, it happened. Google announced it had built a machine that actually did something faster than the world's best supercomputer. They called it quantum supremacy. Let's talk about Grover's algorithm. Imagine you're trying to find one specific name in a massive phone book with 1 million entries, and it's not in alphabetical order. Classically, you might have to check, 500,000 names on average. Grover's algorithm? It can find it in about 1,000 tries. It's a game-changing speed-up.
So, how in the world does it do that? Okay, stick with me here. First, it puts every possible answer into superposition. It's looking at everything at once. Then, this clever little process called an oracle goes in and essentially tags the right answer, not by highlighting it, but by flipping its sign. Then another process comes in and acts like an amplifier. It boosts the signal of that one tagged answer and cancels out all the wrong ones. You repeat that a few times, you take a measurement, and boom, the correct answer is basically the only one left shouting.
But then there's Shor's algorithm.
And this is the one that keeps cybersecurity experts up at night. All it does is one thing. It factors huge numbers. Now that sounds boring, right? But that exact problem, factoring huge numbers, is what makes all of our modern digital security work. It's too hard for regular computers. Shor's algorithm solves it exponentially faster. A powerful quantum computer could theoretically crack the encryption that protects our banks, our messages, everything.
So, okay, breaking codes is the big, scary application. But what about the other side of the coin? This isn't just about math problems. This tech is poised to spark revolutions in pretty much every industry you can think of.
The most urgent one for sure is cybersecurity. The threat from Shor's algorithm has kicked off a global arms race to invent what we call quantum-safe cryptography. It's a massive effort to design new digital locks before someone builds the quantum key that can open all of our old ones.
Now, let's look at medicine. The potential here is just breathtaking. Here's the thing. Nature itself runs on quantum rules. So if you want to design a new drug, you need to simulate exactly how it will behave at a molecular level. Classical computers can only guess, but a quantum computer can simulate it perfectly, letting us design and test new medicines with incredible speed and accuracy. It could change how we fight everything.
And this same power applies to any massive optimization problem. I'm talking about running a global supply chain, managing a financial portfolio, or even organizing traffic in a major city. Finding the one single best answer is often impossible for today's computers. Quantum computers are built for this. In fact, Volkswagen has already used one to optimize bus routes in Lisbon. This isn't science fiction anymore.
So, with all this world-changing potential, it's really easy to get carried away. But we need to pump the brakes for a second. What does the near future really look like? The reality is, we are at the absolute dawn of the quantum age, and there are some huge hurdles to get over. Which, of course, brings us to the question everyone asks, so when do I get my quantum laptop? And the short answer is probably never. And there are some very, very good reasons for that.
You see, building a useful quantum computer is maybe one of the hardest engineering challenges humanity has ever taken on. Qubits are unbelievably fragile. Think of them like a soap bubble. The slightest vibration, the tiniest change in temperature, and poof, it loses its quantum state. We call that decoherence. This environmental noise creates tons of errors, which is why we're in what's called the NISQ era, noisy intermediate scale quantum. The machines are powerful, but they are really, really imperfect.
This is exactly why just counting the number of qubits in a machine is a terrible way to measure its power. Who cares if you have 1,000,000 qubits if they're all noisy and full of errors? So the industry came up with a much better metric, quantum volume. It's a single score that looks at not just the number of qubits, but also how good they are, their error rates, how they're connected, and how long they can stay quantum. It's the real benchmark for progress. And that leaves us with one final fascinating thought, which really captures the two-sided nature of this whole thing. We've seen how a quantum computer could be used to break our digital world. But what if we use those exact same quantum principles to protect it? What if we use that spooky entanglement to build a whole new kind of network, a truly unhackable quantum internet? That's the real promise here. Not just a faster computer, but a fundamentally new, and maybe safer, way to connect our world.